Dr. Ranjani Parthasarathi is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published papers in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on computer networks. Today's lecture will be on the network layer functions. Typical network layer functions that we will be looking at are routing and forwarding, and in routing we will be looking at two routing algorithms, distance vector routing and link state routing. Now if you look at the network layer, we have already seen that network layer performs a number of functions. Two main functions are routing and forwarding. Now what is routing and what is forwarding? Routing is essentially finding a path or a route between source and destination. So I have the source here, I have the destination here, I need to find a path between the source to the destination. Now multiple paths may be available, I need to choose the correct path between the source and the destination. So we need to find, as I said, a suitable path for a packet from a sender to a destination. So this is one possible route. If I have this network here, the one shown in blue now is one possible route. Now you could have another possible route which could go like this. So the idea is in choosing the correct path. So that is what we need to do. Now a router now therefore may need to choose between two or more paths that lead to the destination. Typically what we do is we choose the shortest path. Now when we say shortest path, the shortest could be in terms of the number of links that have to be traversed, or it could be in terms of some other cost function, in which case we would say we would choose the minimum cost path. The cost could be dependent on bandwidth, it could be dependent on the data rate and many other factors. But in general when we say shortest path, we mean the least cost path, or we would rather use the term shortest path to mean any of these. Now typically there are multiple hops to make the journey. So unless the hosts are on the same network, you will have to go through multiple hops. So choosing the path through different hops is what is the job of the router. Okay. Now once you have done this routing, a routing algorithm is used. It is part of a network layer software and is responsible for deciding which output line a packet should be transmitted on. So once you have the routing algorithm which is already decided on the network on what is the path to be taken, what happens in forwarding is when the packet arrives, you just take it, consult this information that has already been obtained from the routing table, from the routing protocol, and consult that information and just forward the packet to the correct destination, that is the correct output line on which this packet has to be transmitted. That is what we mean by forwarding. So forwarding is when data is received, forwarded towards the destination. It is a very simple process. There will be multiple ports which any router or a switch will have. So choosing the correct switch or choosing the correct port on which it has to be sent out, that is what is done during forwarding, and this is done only when the packet is received. So who performs these network layer functions? That is done by switches and routers, and how are these functions carried out? This is what we are going to look at now. So now this is what the architecture of a router would look like. So if I am looking at we are typically looking at routing algorithms which are used in packet switch networks. So what you would have is you will have a switching fabric which is the central switching central part, and a routing processor which determines how this switching fabric is going to work. There are input ports on which different packets come in, and there are output ports. So you have to determine from which input port to which output port it has to be sent. Now the packets coming in on these different ports would have the information, the destination address in the headers of these packets, and by looking at the destination address, the switching fabric and this routing processor will determine on which output port it has to be sent out. So this is what is the actual architecture of a router. Now if we are using circuit switching, in that case you may not have these input ports and output ports, but you will still have a switching fabric and routing processor which will be responsible for identifying the paths which are set up during the connection establishment phase itself. But our concentration now is more on the packet switching networks. So we will be looking at a situation like this where you have input ports and output ports. So forwarding essentially in this scenario is taking it from one input port and putting it on the correct output port. Now coming to the routing algorithms, there are two popular algorithms which are in use today. Both are distributed algorithms. One is called the distance vector routing algorithm and the other is called the link state routing algorithm. Two protocols which are currently used in the internet network today are basically based on these two routing algorithms. Now let us take a look at the distance vector routing algorithm first. It is a very simple algorithm. What it does is, each node in this algorithm constructs a vector of distances to its neighbors and transmits that information to its neighbors, and this information is used for building the routing tables. So this is what happens in distance vector, that is, each node will just look at its connectivity, what are the neighbors to which it is connected, and it forms a vector which has the distance to its neighbors and transmits this to the neighbors. This information is what is used to build the complete routing table. In link state routing algorithm, a different approach is used. So here what you do is, you disseminate the link state information of neighbors to everyone in the network, that is, you are sending it not just to your neighbors, but you are sending it to all the nodes in the network. And then routing tables are constructed based on the sum of information from all the nodes. So we again use sum of information from all these nodes, and that is what is sent to all the nodes, and all the nodes now will construct their routing tables based on this information. Let us look at distance vector routing in detail. So what happens in distance vector routing is, each node will maintain a set of triples, that is, destination, cost and next hop. The destination to which it is supposed to go, what is the cost to that destination, and through which next hop or through which next neighbor it has to be, that particular packet will have to be sent. This information is maintained as a set of triples. Now this information, and what we do is, you exchange updates with directly connected neighbors periodically, that is, and this periodicity could be of the order of several seconds or whenever there is a change in the table. Now this is called as a periodic update, the first one. The second is called as a triggered update, that is, when a trigger happens because of some change in some information, that causes the table to be exchanged. Okay, so this is the basic idea. So you have some information and you exchange that information with your neighbors. Neighbors use that information and update their values and pass on that information to their neighbors and so on. Okay. So each update that we have is a list of pairs, destination and cost. So every node will say, I can reach this destination at this cost. This information is sent to the neighbor. Then you update the local table if you receive a better route. Okay, that is, if you receive a better route, a smaller cost comes from the next hop, then you can update your local table. You refresh existing routes and delete if they time out. This is the basic idea that is used. Let us take an example here. Let us look at what is happening here. If I have some network, A is connected to network number 14, which is also connected to router B, and then network 55 is connected to B and C, network 66 is connected to C and D, and so on. Now what every node here does, every router here does is, it says, I periodically send my knowledge about the whole network to my neighbors. So B, for instance, will say, I will send it to A and C. C will similarly say, I will send it to B and D. D similarly will send it to E and C. F will send it to A and to A alone, that is, it has only one neighbor here. A on the other hand has got three neighbors, B, F and E, so it sends it to B, F and E, right. So this is the basic concept that we are using in distance vector routing algorithm. Okay. So the distance vector routing table will look like this. It has a network ID, cost and the next hop. Okay. Out of this, what it sends to its neighbors is the network ID and the cost. Only this part of the information will be sent. Okay. So let us look at the same example again. So now to start with, look at the information that A has. A is connected to three networks, network 14, network 78 and network 23, right. So what it does is, it says that I can reach network number 14, 23 and 78 with a distance of 1. Okay, this is the information that A has. Now there is no next hop here because these are directly reachable from A. Similarly, B has this vector here which says 14 I can reach within one hop, 55 within one hop. Similarly, each of these nodes will have this information that they collect. This vector is now passed to the other neighbors. Now it does not know about other neighbors, right. So those you can look at those values as being set to infinity. Okay. So now let us look at what happens. Let us look at the routing table for router A. Okay. How that gets updated when it gets some information from B, right. So just remember this, B has this information that it can reach 14 with network 14 in one hop and network number 55 in one hop. Okay. This information is being sent to A. Now look at what A will do. A receives this 14 that it can reach 14 with one hop and 55 with one hop from B. A already has its original table. So now whatever it receives from B, it knows that B itself can be reached only at one hop. So it adds that one hop distance information to this. So after this adjustment here, the information getting from B, it gets that 14 can be reached with a distance of 2 hops from B, 55 again can be reached at a distance of 2 hops from B. Now A already has its old table, so this table and this information, these two now have to be merged together, combined to form a new table. And when you make this combination, you identify those paths for which you have a lower cost. So you can see that with respect to network number 14, directly you can reach it from A, whereas through B you have to send it to B and then again back to 14. So this has a cost of 2. So out of these two, I will retain the first entry. So my A's new table will have a value of 14 can be reached directly with a distance of 1. Now there is and about 23 and 78 there are no change, but you are having some new information coming in from B, which is that B can reach network number 55 and the distance would be 2. So that information is added in A's new table. 55 to B is a new information that is added at the end of this first exchange that is taking place between A and B, right. So similarly now every node will keep exchanging this information with all the neighbors, and at the end of this entire routing process, of this entire information exchange process, every node will construct its routing table. Okay. So every node when it constructs the routing table will have reachability information for every network that is there in this entire network. So you can see that A will finally say I can reach network number 8 in 2 hops through E, right. So this is network number 8, it can be reached through E. This information I have got after exchanging information with E. So remember that A gets, we just saw an example of how A updates its table when it gets information from B. Now similarly it would have got information from E and F as well. E similarly would have got information from D and A. So you can see that each of them now will be able to construct the complete routing table information, that is identifying the next hop through which they can reach a particular network. Okay. So so if you look at the table at A, it says that I can reach network number 8 in 2 hops through E, 14 directly 1 hop, 23 directly 1 hop, 55 through B 2 hops, 66 through E 3 hops, 78 directly, 92 2 hops through F. Okay. So this is the information that will be there at A. Similarly each router has the final routing table. Now it is this routing table that is consulted when the forwarding needs to take place. Alright. Now when any change happens, the change also will cause the entire routing table information to be updated. So let us say for instance original message from C was that network number 2 could be done in 4 hops, network 3 in 8 hops, 6 in 4 hops and so on, and there was a change that all these got incremented by a value of 1. Okay. So there is net 2, it says now can be updated in 5, can be reached with a distance of 5, 3 in distance of 9, 6 with a distance of 5 and so on. Now if this was the old routing table that was available, when this message comes from C that this increment has happened, that some change has happened, there is also an updating algorithm which will take place, which was basically as soon as basically rerunning whatever we had just looked at, and based on that you will decide that a new routing table now needs to be constructed with this which has incorporated this additional information. That is, whenever there is a change with respect to C, right, whatever information came from C, that information is what will be changed based on this update that is received from C. Okay. If there is no information about a particular network in this advertised message, that particular routing table information will not be changed. For instance, in this message that is coming from C, there is no information coming from about network number 1. It only has information about 2, 3, 6, 8 and 9. And in the routing table, I only have information about 2, 6, 8 and 9. So they will be changed based on what I get from C. But network number 1, there is no change because there is no new information that is coming from here. So based on the new information that comes, this updates will update the corresponding routing table. Okay, this is what happens in the distance vector routing algorithm. Now there could be some problems in this particular algorithm. Now basically we can see that if you look at this figure, back at this figure again, now depending on the maximum distance that you have between various nodes, which we can say is the diameter of the, if you represent this entire network as a graph, So, you can see that that is what all these routing algorithms do. So, what they do is they basically represent the entire network as a graph and try to identify the path along this graph to go from any node to any other node. So, now if you look at the maximum distance, whatever, suppose let us say D is the maximum distance that I have from any node to any other node. Now, in that many exchanges you will find that everybody will get information about everybody else. Okay. So, that is the kind of time that it takes for all of them to converge to the final information about reaching all the other nodes in the network. So, we will take a small break now and then come back and look at further details of this protocol. Welcome back after the break. So, we have been just looking at the distance vector routing algorithm which is used at the routing layer in routers in packet switch networks. So, in the distance vector routing algorithm we just said that every node maintains a vector of its distances with and to different networks and passes that information to its neighbors. So, it just exchanges information with its neighbors, and for this exchange to cover all the to go to all the nodes in the network, it will take maximum whatever is the distance, maximum distance you have in the network. Within that many exchanges they will all get information about all the nodes in the network. Now, there can be some problem with this kind of a exchange mechanism because only local information is exchanged locally, that is you exchange this only with your neighbors. There are some problems that can occur. So, let us just take an example of one such problem. Let us say I have some network like this, right. I have node 1, 2, 3 and 4 which are connected in a linear fashion like this. Okay. Let us assume that this particular link 3 to 4 fails. Assume now that the cost for each of these is just 1. So, if you look at what this routing table will be before the failure and after the failure, we can see what will happen. So, now with respect to connectivity to this node number 4, let us look at what is the information that will be maintained at 1, 2 and 3. Node 1 before the break would think that it can reach this particular node 4 through node 2 in 3 hops, 1 plus 1 plus 1, right. Node 2 similarly will have information that it can reach it through 3 in 2 hops. Okay. So, node 3 similarly has a direct connection to node to 4 with a distance of 1 hop. Now, this link 3 to 4 breaks. So, what will happen? 3 immediately has no connectivity to 4, therefore, it will set that value to infinity. Okay. So, now similarly, now look at node this sets it to infinity. So, 3 comma 2 is the value that is available at node 2, 2 comma 3 is the value that is available at node 1. Now, after some time there will be an exchange of information that is going to take place. Now, we know that periodically they exchange information as well as because of this trigger that something has changed, there will be a change of information. Now, look at what will happen now. This 3 comma infinity information will cause this information to be sent to node number 2. Now, when node 2 receives that information, what will it do? It will have to update its value to infinity, right. So, meanwhile, let us look at before that what will happen. Before that it is possible that 2 sends its distance vector to 3, and according to this 2 says that I can reach 4 with a distance of 2, right. This is the information that this will be sending over here. Remember that when this is sending it over here, this is sending it over here. So, if both these things cross each other depending on the timing at which these exchanges take place, it is possible that 3 comma 2 information comes over here, and when this information reaches over here at 3 basically compares the information it already has, which says the distance of infinity to 4, whereas now it is getting a path through 2, right, and its distance to 2 is 1. So, at a distance of 3 now it thinks it can reach node number 4, that is it assumes that it is getting some information from 2 which says that 2 says I can reach node 4 in 2 hops. So, 3 thinks maybe there is alternate path available somewhere like this and says okay, I will update my table to 2 comma 3, that is it thinks it can now reach node number 4 in 3 hops. Okay. Now, subsequently look at what will happen. This information again will be sent back to 2. Now, since 2 already had received information about 4 from here, it could make this update and change this to accordingly, yes, because this distance now has become 3, it will make it 4. Now, this information similarly will be passed on to node number 1. So, node number 1 will now change its value to, since originally it was it now has a distance of 4 plus already a 1 hop distance to 2. So, it will make it as 5. Now, look at what should actually be happening. What should actually be happening is the moment 3 comma 4 becomes infinity, all these people must immediately get the information within the next few exchanges that distance to 4 is infinity, because there is no connectivity to node number 4 at all, right. In this network there is no connectivity to node number 4. Now, whereas you can see what is happening here, they are not getting it immediately, but they are all slowly getting increased values of distance to node number 4. So, you can see this further. Now, from this 3 comma 4 causes the next exchange here to become 2 comma 5. This 2 comma 5 when it comes over here causes this to become 3 comma 6, which in turn causes this fellow at node 1 to become 2 comma 7, and this also to become 2 comma 7. So, you can see what is happening here. Slowly they all start counting all the way up to infinity. So, this is called the count to infinity problem, which is one of the major problems that we have in this distance vector routing algorithm. Okay. So, how do we solve this distance vector routing algorithm? So, basically what we do is, there is one mechanism that is used, which is that you set this infinity value to some large value, typically a number like 16. So, which means within 16 exchanges you will anyway count all the way up to 16, which means you have counted up to infinity, and you would have identified that there is no path available to that network anymore. Okay. So, that is one possibility. Another is what is called as a split horizon technique. Now, here what happens is, look at what the problem was over here. Now, the problem was that 2 after all received information about going to 4 only through 3, and when 3 reports a value of infinity, there is no point in 2 telling 3 again back to 3 saying that, oh, I have a path toward to 4. After all, that path is only through 3, right. So, the idea that we use in the split horizon technique is that we will not exchange information that I received from somebody back to that same person itself. Okay. So, that is what we do in the split horizon, that is, you do not send minimum cost to neighbor if that neighbor is the next hop for that particular destination. Okay. This is the idea that is used in split horizon. So, naturally what will happen in this case, 2 would not have given that information back to 3. So, naturally 3's information will propagate to 2 in the next step. Similarly, 1 will not give back information to 2. So, 2's information will propagate to 1 in the next step. So, within 3 steps all of them would have got the value of infinity. So, this is how the split horizon technique works. Okay. Another mechanism that is used is split horizon with Poisson reverse. Here what you do is you send minimum cost to all neighbors, but you set infinity to the next top neighbor. Here we say we do not send the information, whereas here what you do is you send the information, but you set that value to infinity. It is called as split horizon with Poisson reverse mechanism. So, these are mechanisms that are used in order to solve this count to infinity problem. But again, split horizon technique also you will find will fail when you have loops with involve more than 2 nodes. So, we still have a problem with this distance vector routing algorithm, but it works because we use these techniques of setting infinity to 16 and so on. Only problem is that it takes a longer time to converge to the final value. So, that is the problem. Otherwise, we can still work with this distance vector routing algorithm, which is why it is still used, which is why we say it works satisfactorily in some cases. Okay. In some cases it could take a longer time to converge, but in most cases it would work. Okay. I am just going to give you another example of the same distance vector routing algorithm. So, let us say we have this network here. We want to construct the routing table using this distance vector routing algorithm. I am giving you different values for the different links over here. In the previous example we had taken distance of 1. In this we are just assigning different costs to the different links. So, let us look at how this will work. The algorithm is the same algorithm. So, I am just showing initial vectors that you have at each of the nodes, right. So, let us say at A, B, C, D and E, right, these will be the initial vectors. A will say I can reach A with a cost of 0, B with a cost of 1, C it does not know any information about C, so let us set that to infinity, then D with a cost of 2, E again is set to infinity because there is no direct connection between A and D. Now, B similarly will say I can reach A and C. So, to A, C and E it has information that can reach with 1, 15 and 5 as the distances. To D is set as infinity. Similarly, you can see that C it will be infinity to A, 15 to B, 0 to C, 1 to D, 10 to E and so on. Okay. Now, let us look at what happens after the first exchange, right. At the first exchange, what I mean by first exchange, A will receive information from B and D, B will receive information from A, E and C, okay. C receives from B, E and D, D from A, E and C, E from D, C and D, right. After this exchange of information that takes place, or the first exchange as we call it, let us look at what will be the distances that you have. Now, A to 0, with respect, if I look at what is happening at A, similar thing happens at B, C, D and E. So look at what happens at A. A's initial value was A to A was 0, A to B is 1, no change in that. A to C, now this is new information. Look at what it will get from both B and D. B would have reported distance of 15 to C, D would have reported distance of 1 to C. Now A's distance to D is already 2, so it will add up these two and say 2 plus 1, 3 is my new distance to C. With the update from B will be 15 plus 1, 16 as the distance from B. So it chooses D as the next hop to C because this has a shortest path. So that is the reason why I have given you taken this example. So you can see 3 comma D will be the value that you have at C for C. So distance to D is 2, which remains the same. To E again you can see it will get both from B as well as D, and again you can see that through D it has a distance of 4, whereas through B it will be a distance of 6. So again it chooses 3 comma D as the information that you have over here. Okay. So this is after the first exchange. You can see that these are the values that you have at each of the nodes. Now you can see that in all these cases you have got the values for almost reaching every single other node that you have in this network. But is this the actual optimum value? Not so. You can see that after a second exchange there will be a further stabilizing of the route. That is, you can see what is going to happen here. To go from, if you look at this figure, to go from B to C, I have a direct path at a cost of 15. I also have a path through E at a cost of 5 plus 10, which is 15. But I also have another path through A, which will actually go from A to B 1 plus 2 3, 3 plus 1 4. This will be actually the shortest path, right? You actually have one more path. You have from B to E to D to C. This is 5 plus 2, 7 plus 1, 8. But of all these 4 paths available, the path through A and D is the shortest path. So you can see that B's distance to C should actually become 4 through A. Now that will happen after the second exchange. After the first exchange you can see that B has a distance of 15 to this, whereas now after the next exchange, when A reports a distance of 3 to D, B's distance to A is already 1, so 1 plus 3 will become 4. So this is what you will see happening in the second exchange over here. So after the second exchange you will actually find that the shortest path that you have is obtained, right. So this is how the distance vector routing algorithm works. So to summarize, let us look at what we have looked at today. We have looked at the idea of routing and forwarding, and in routing we have looked at one particular algorithm, which is the distance vector routing algorithm. We saw how this basic algorithm works, and we also looked at the problem that it could run into, the count to infinity problem, and we also saw a couple of solutions to that problem. And we saw how this can be used for arriving at the minimum cost path. A few questions for you to review what has been done today. What is meant by routing? Question number 2, what is forwarding? Question number 3, what is the idea used in distance vector routing algorithm? Question number 4, what is the problem with this algorithm? Question number 5, what is meant by split horizon technique? Thank you.